So good morning. Yeah, I think that welcome to join the training. Today we're going to talking about the V6 refrigerant system. That I hope after this training you have a better understanding of our refrigerant circuit, how to make this system work by the principles and the key components working together with our control logic. Okay, so the slide here, we can see it have 5 parts. First one, it's the refrigerant system. First, if my voice is not clear or something, that you can open your phone and let me know. Second part is the key components. Third part will be some control logic, and then we will take a look at the special operations. Last part I deleted is some function of the new indoor. I think we will pay attention to the refrigerant circuit. Okay, so speaking of the refrigerant circuit, that for key component, I think everybody is very familiar now because we have holding this training, I think several sections till now. So for key component, compressor, outdoor heat exchanger, indoor heat exchanger, EXV. How they work together. Here we take an example, it's our 32 horsepower unit refrigerant circuit, how the refrigerant is flowing in the system. Here it's a compressor, right? The pen. Here it's the compressor and oil separator. This is the exchanger, indoor side, and here some expansion valves and the plate heat exchanger, accumulators. Compared to our nominal, for example, V5X, the V6 platform that we have a new additional one is the plate heat exchanger here. And another one is the compressor, right? For our nominal one, we have one inlet and one discharge and one suction back. But for V6, that's the compressor, we have the EVI, right, function. So it has the third hole to do vapor injection. Here we can see it's the orange, the color is orange, right? So this is the difference. Okay, so from this drawing that we can see we have total 4 indoor units, and 2 of them it's running in cooling. We know that for an air conditioner, it's working by use the refrigerant different phase to absorb or release the heat to do heat exchange with the ambient temperature indoor side. So that's how we can realize the whole system working, and by the help of a compressor, so the refrigerant can flowing from the indoor side to the outdoor side, from outdoor side to the indoor side. So here, first the compressor will work, then the high temperature and high pressure refrigerant will be discharged out of the compressor. First it will reach to the oil separator, because when the refrigerant spray out, that a little amount of oil will be take out along with the refrigerant too. So we need to get the oil back. So here we need to have the oil separator. Then in cooling the first, here the foil valve, it's used to realize the mode change, right? If in cooling, then here we can see that it will enter, the refrigerant will enter the outdoor heat exchange first, and do the heat exchange with the outdoor ambient temperature. This process, it's a refrigerant phase, turning from gas into liquid. So when the refrigerant is coming out from the outdoor heat exchanger, normally it will turn into high pressure, but the temperature is the middle one, liquid. And then here we can see it will keep going, and then we'll enter to the plate heat exchanger. Plate heat exchanger, we can say that it have two functions. In cooling, it's we can take it as we have a small additional outdoor heat exchanger, so it can help some cooling. So here, after the heat exchanger, then we will, here it's a little new box if saying for V6 unit that under this design of the electrical box, there is a small route of refrigerant pipe will go to the back of the electrical box, so it can take away some heat from the control box and make sure the control box can be cooled down and keep the electrical component working more reliable. After that, then the refrigerant will go to the indoor EXV. We all know that the EXV is very important in the system because we need it to do the throttling, get the pressure down and get the temperature down. So after the EXV, the refrigerant will be low pressure and low temperature, so it can with the working with of the fan. This is the off. This two. Then the low pressure, low temperature refrigerant will be easily do heat exchange with the high ambient indoor side air, so the room can cool down. And after absorb the heat from the indoor side, the refrigerant will goes back to the compressor and another cycle after one another, so we can realize the cooling mode. Okay, heating it's help due to the four-way valve. So it's similar. It's just after the compressor discharge the refrigerant, it will enter directly into the indoor side first. So the low indoor ambient temperature can do heat exchange and the indoor room can heat up. So here we can see there are lots of valves to it. We all have this design. We will introduce later the valves and the components. We can see this. We have a design principle, right? And with the design principle and with all the components and the pipe loop connection and the control logic, so we can make a machine can realize the cooling and the heating. Okay, the next part we will take a look at the key components. Here we can see we will introduce the compressor, the plate heat exchanger, the pressure transducer, all things called pressure sensor, and a pressure switch for a valve, EXV, solenoid valve, and the oil separator and the accumulator to see how they work in our system. Compressor, no doubt it is the key component of the whole system. For V6 unit that we adopt the Hitachi EVI compressor as I mentioned, which can help subcooling in cooling mode and can help we know that when the low ambient temperature that the refrigerant volume in the system, because the heat exchange is not good, so the whole system volume will not be much. So that's why low ambient temperature, the heat capacity is not, performance is not good. And the EVI compressor can help with that. It's by the third hole we mentioned, the vapor injection left function. So the middle temperature, middle pressure refrigerant will get back to help to improve the heating capacity when the ambient temperature is low. Okay, so here we can see V6, the whole series, we adopt two type of compressor. One we call it model 80, and the other one we call it model 55. So here we can see for smaller models, V6 under 16, that we adopt one compressor, and from 18 to 32 horsepower that we adopt two. This is for the combined. The one can be combined. Here we can see that for individual one, 18 horsepower, we only use 180 compressor. Here, it's an inner structure of the EVI compressor. Here we can see this is the discharge. Here it's the suction back and this is the vapor injection one. We adopt the scroll compressor, right? The DC water scroll type. I think that we'll know that for EVI compressor, this one, that we adopt some technology. Here we can see, for example, like the concentrated motor, and it have a release valve. So with the technology improved, so the EVI compressor make it more suitable to running in middle low frequency, and the operation range of the compressor can be more larger. Max can be 140 RPS. And the other one is the technology I mentioned, that the third hole, which can make the heating performance much better in low ambient temperature. Okay, because as compressor is a very key component in the whole system, and if it's breakdown, that the system will break down. And another point is that the price of compressor is the highest in the system, so we don't want to get it damaged. So we will do lots of protection to avoid the compressor directly breakdown. Here we can see we have the P3, we call it compressor protection control, which means that when the compressor current is over our limitation, here we can see for model 80, it's 33 ampere. And for model 55, it's 24.6. So if the compressor current is over, then we will have the protection code showing. Okay, so here it's a track steps for how to measuring the resistance of the compressor. In the IOM, or not IOM, in the service manual troubleshooting part, normally we will put this introduction to tell when something like P6 or H4 error code is showing, then how to measuring the resistance of the compressor to see if the value is in normal range or it's out of range. Here you can see this two 0.925 ohm. But normally when compressor and when the system is down and it's related to the inverter module, that normally it will have several possibilities. The simplest one is that the control box has some problem. Then we find which board is failed or which wire is not connected, so we can reconnect or replace with a new one. Second one, it's sometimes the power supply, it's directed, power supply has problem, and then there is another possibility, the compressor itself has some problems, so the inverter module cannot drive it. So so we need to analyze when some system breakdown. Okay, then we will take a look at the pressure and therapy diagram. Maybe I'll just tell it more simple, because this is the principle of the reference circuit. We can see that we can just take this photo as we have 4 phases in the whole system. This would be the compressor do the compressing from here to here. It's what happening in the auto heat exchanger. Let's do the condensing, and then this is the throttling phase. So it's the EXV part, and this is the indoor heat exchanger. So we'll do the evaporating. So this is 4 phase. This is the condensing temperature. Here it's the evaporating temperature, and this is a normal one. So we can simply say that here it's as showing the EVI phase. So it's a little different, and here it's the subcooling. The initial one will be this. With the plate heat exchanger, we will enter into G. And here it's we have a small amount of refrigerant by the vapor injection hole, so the initial refrigerant volume will get mixed with the vapor injection one and do the compression together. So here it's just a principle to say that with the EVI compressor compared to the one do not have this function, how is it help for cooling, and how is it help for heating in low ambient temperature? Okay, the whole system to make the refrigerant flowing in the system. That the compressor it's the energy power source. So here we can say take a look at how it's the compressor control logic. First, we know that although it's it's not the one we tell it how to run, right? It's from the indoor side. The customer will send the parameter settings. What is their target, their mode? What is the temperature they want, fan speed they want? And our R&D people have it. We can call it the capacity demand calculation inside. It's not based on the settings from the customers. Then that the PCB will got what is the total capacity demand from the indoor side. Then the indoor side will send the signal, do the communication with the outdoor PCB by PQE wires. Then the outdoor will know what is the indoor side demand, total, how much. Of course, it will be some revisement based on the ambient temperature. Then the outdoor will sometimes we'll have a master one, we will slave one. So the outdoor master unit, it will have some logic to tell. In this time, I run only one unit is enough, or I will need to run the whole system. Which frequency each outdoor need to operate, so the indoor side can meet the demand. So here we can see it's the response for the outdoor compressor in the startup. But here we can see it's the target frequency. It's not reached in once. It's separated in several steps because we wanted to keep it more reliable for the compressor to run. Okay, so this is when the compressor starts. Then when will the compressor stops? Here, let's take a look at the compressor start. We can say standby or or turn on, turn off logic. Normally that we can see when the indoor side there is no capacity demand. That is mean my setting temperature reach the my room temperature reach my setting temperature. So at this time my compressor need to stop. But when we do the from my personal understanding that I think for keep the system more compressor, more reliable, that we design a 1 degree tolerance in the control to avoid the compressor frequently starting and turn off. Which means here and another one is because different people have a different feeling. For example, in heating, when the hot air normally is on the top, so the area where people standing, that's the temperature, it's not reach what is the setting of the customer. So we will have we call it compensation design in the PCB selection by some dial switch here. This is for cooling mode. For heating, we have the 0 to 6 degree compensation for customer to select to. And for we can see that, for example, in cooling, that on the right side, it's running cooling. On the right side, it's standby, which means the compressor will stand by. So it should have something like this. T1 is the room temperature. Ts it's my setting temperature. So when it's here it's the compensation. For example, here we can take it as delta T. If for cooling mode it's 0, then it's 0. There is a 1 degree tolerance. If reach this, so T1 minus Ts, if it's larger than 0 plus, right? Plus delta T. Delta T default from factory is 0. So here it's 0. Then the system will run cooling mode, which means the compressor will start. But when T1 minus Ts is smaller than -1 plus delta T here, when I didn't set anything, it's 0. So if reach this condition, then the compressor will stop. So this unit will be standby. So this is just one example. Okay, then let's take a look at the plate heat exchanger. In cooling mode, the plate heat exchanger can help the subcooling. So the refrigerant can achieve better heat exchange because the temperature after the plate heat exchanger will drop more. So it will help more when the refrigerant reach the indoor side, so it can absorb more heat from the indoor side. The EXVC is used to control the superheat. If the superheat is too small, for example, then the open degree of the EXV will be closed. It's controlled according to the tolerance of T6B and T6A, inlet and outlet temperature of the plate heat exchanger. Okay, so the previous one, we take a look at the compressor, and the compressor turn on and turn off logic, and the plate heat exchanger. But for a refrigerant that we wanted to keep it more stable running and in good performance, only the 4 key components it's not enough, because we have lots of parts needed to working together to realize the control and protect the system too. So then let's take a look at some key components too working together in the system. First of all, here we can see it's the pressure transducer. We can call it a pressure sensor. It's used to detect the system pressure and realize the fan speed control and protection of the system. It can turn the system pressure into voltage, DC voltage, and after here we can see Bayer formula. This is formula. So the pressure will turn into voltage, and the voltage can send to the PCB. So the main PCB will tell in this time my system pressure if it's in the normal range or not. So this is the pressure sensor. Pressure sensor is used to get what is the system pressure now. But sometimes that even I can detect what is the system pressure right now. But sometimes suddenly then maybe there is some something happened. So the pressure in one time it increase a lot and or drop a lot. So this is why we design our pressure switch too, because we don't want to have this situation happen, because it will damage the system. But when we design a system, we will have normally we will have a target pressure that we try to make the pressure in a certain range, and it's better for the compressor too, better for the energy efficiency ratio too. So here, when we design the high pressure switch and the low pressure switch, it's to in case that sometimes the pressure is out of control, out of range. So we have the pressure switch. We can stop the system and to protect the system. Here we can see high pressure side we have one, low pressure side we have one. If the pressure is higher than 4.4, then we'll reach to our high pressure protection. When the low pressure side, the suction pressure it's lower than 0.05 MPa, then it's over our limitation. Then we will have the P2. So the compressor will stop first, but it will recover. Because my compressor stopped, so the system is not working. So after some time, the system will pressure will recover. High it will turn low, and low it will turn to higher one. So the system will be fine. But normally 3 times, then it can not start automatically. Need manually start. Okay, here it's saying for Europe, but we are forced for Europe market that the high pressure is 4.2, not 4.4. Okay, so let's take a look at the pressure switch inner structure. Here we can see one is the high pressure and the other one is the low pressure. Working principle. Here we can see it's a little, this is the initial state. Here we can see the left side, the 2 pieces, it's stay together. When pressure increase, so the rod will be lifted. So, and it keep, if the pressure keep continue raise. So here we can see that finally this 2 piece will be separated, disconnected, so it will enter into the protection state. Okay, so this is the high pressure and the low pressure switch for protected the system. We just mentioned that for V6 heat pump that it's heating and the cooling mode we all wanted to realize. So for valve is very important because it's used to switch to heating mode. Here it's an inner structure of the foil valve. Let's take a look at this one. Normally it has 2 parts we can see. This is the main body. Here is the main body. And this is the, what call it? It's like a guider valve. We need the coil to realize the change direction of the smaller one, so it will change the direction of the refrigerant. In cooling mode, we just know that the foil valve we need to build a pressure difference in the 2 sides of this main body valve. Here in cooling mode, this side, it will get the refrigerant from a compressor, right? So the refrigerant will push the right side. This what I can call it, the chamber pilot side of the valve. Just by the design of the valve, the refrigerant will pressure this right side will be higher than the left side, so it will push it go to the right side and finally reach the status. So after reach this status, then we can see the main refrigerant will come into the main body. After the main body, so it can first go to the auto heat exchanger and do the heat exchange inside and go back from the, here we can see from the left pipe and go back from the middle pipe and go back to the compressor. And for heating, it's on the contrary, by the coil. So we can see here the direction, the connection of this three pipe is changed. First it's this one, and now in cooling it will tend into this two connected together. So by this, it will make the right side will be the high pressure one compared to the right side. So the refrigerant will push the guide in the main body from left goes to the right. So this half cycle will finally connected as this way. So the refrigerant from the compressor will enter into the main body. So in cooling mode, in heating mode, it can run first into the evaporate the left pipe and goes to the indoor side to the heating. After that, so it will go back to the right side pipe and from the middle pipe. So we can see no matter in cooling or heating mode, the middle one, it's the suction pipe, so the temperature of it will not be high. Okay, so here, four-way valve main functions. It's used to control refrigerant flow direction, closed in cooling mode and will open in heating mode. When closed, the heat exchanger will work as a condenser. When open, the heat exchange will work as evaporator, so it can realize the cooling and the heating mode change. Okay, four-way valve. Then it's for the mode switch. Then let's take a look at the EXV. EXV, its function is to use to control the refrigerant volume and the pressure by adjust the open degree of the EXV. Here it's an inner structure of the EXV. Here we can see there is a small core inside of the EXV, and there is a rotor coil. It's controlled by the electricity. By this coil, so it can realize the open degree adjustment to control the refrigerant volume or refrigerant flow in the system. Here we can see some EXV models that in V6 and the V6 individual one, we adopt in different models from 8 horsepower to 32 horsepower. Normally it is 480 steps. Some is 30 steps. EXV, EXV, it's especially the indoor side, it's very sensitive. That's why when we do the commissioning, that we will not first, this will keep the indoor not connected with the copper pipe. It's that we do not want the impurity thing get to the indoor side to lock or jam the EXV because it's very sensitive. And normally that we will have some filter before the EXV to filter the impurity first and make the EXV work more longer. Once when the EXV is blocked, similar as the 4-wheel valve, that normally we will see you can try to knock and to see if it can recover, or you can check on the main PCB board to see if the output is normal or the resistance is normal. The auto EXV, I think mainly not too much feedback that it will be broken or something, because the open degree of the auto unit normally it's not so small, as the auto EXV is not for dual throttling. Normally it's just to adjust the refrigerant volume. But the indoor side, it's very sensitive. When you are wondering if the EXV is not working properly, if you can use your hand to feel, then the inlet and the outlet, if it's working normally, it should have some temperature difference. If it's not, then it should have some problem. Okay, here it's a way to measure the resistance of the EXV to tell if it's working normally or not. Okay, so EXV control. Here is a table for the auto unit EXV. Slave 1, slave 2, and slave 3. So here we can see when the unit is in standby, the EXV will be at 352 steps. When the unit is initial power on, it will first goes to 0, and then it will be the standby position. And when the system is running in cooling mode, how it will be controlled for cooling. It's according to our discharge temperature. In heating, it's according to the superheat. Here it's a dynamic photo for explaining how the EXV will work, the core inside of it. Okay, when the beginning of our slide that we have seen the refrigerant circuit of the V6 32 horsepower unit, we see there are lots of valves in the drawings. Here we will introduce them one by one. Here it's EXVC is what we have mentioned. It's the inlet and the outlet. It's control the superheat of the plate heat exchanger, and it's adjust according to the value of these two. And normally here we can see the range we need it to be at from 5 to 8 degrees. When the superheat is too much, the valve will open. When the superheat is low, then the valve will, for example, close. Okay, that one is EXVC. We EXVC and the EXVA and the EXVB, it all can adjust the open degree, right? But we have some other solenoid valve like SV4, SV5, and vapor injection SV8, right? This solenoid valve, it's important in the system too. The difference is that it can only be open or close. Here it's the inner structure of a solenoid valve. Let's see the right side. Here, this is the inlet, right? Working with the spring. So in this time it's closed, so the outlet there's nothing. But when the spring is working, then the door is open, so here the refrigerant will come out. When the coil is power on, the spring will be suck up, so the refrigerant can get through. Here it's one tips need to pay attention to. It's the direction. Side in, bottom up, bottom out, not bottom up, bottom. Especially when the system need to do some maintenance after repair, then the direction need to pay attention to. Okay. So here, first one is our solenoid SV4. SV4 is connected to our oil separator and our compressor suction pipe. It's designed for, here it's mentioned, used to return oil to the compressor. When the system is working, that it will first work for 10 minutes. After that, every 20 minutes, it will open 3 minutes for oil return, like this logic it's showing. SV5, it have more functions. It can here enable the fast defrosting in heating, and it can unloading in cooling. During the defrosting, the valve will open to shorten the refrigerant flow cycle, and can quick the defrosting process. And another one is it can spray a small amount of liquid refrigerant to cool the compressor tube when for example, the discharge temperature is too high. Okay, SV6 it's working with the two outdoor EXV valve, EXV-A and the EXV-B. SV6 can allow the refrigerant to bypass the expansion valve. In cooling mode, that it opens when the discharge temperature exceeds the limit. But in heating mode and standby, it will close. SV7 is not all the model have this valve. Here it's mentioned it's only for the model 80 compressor, because the model 80 compressor capacity is more bigger. So when the indoor side capacity demand is not much, it's small. So the compressor may face frequently on-off by the SV7, so it can bypass the refrigerant, so it can drop the capacity output, so can keep the system running more without frequently stop the compressor. SV8, it's in the vapor injection pipe, right? Normally it's help to get middle pressure and the middle temperature refrigerant back to the compressor to help the cooling, not cooling, heating capacity. SV9 is for the system that has two compressors. It's from the suction pipe connected to the second pressure discharge pipe, right? So the second pressure, before the second pressure starts, the SV9 will start. It's designed to balance the pressure and drop the compression ratio. Okay, that is all the solenoid valve in the system. What is their functions? We design it. Then let's take a look at some. This one. First one is the oil separator, something like tank. First one is the oil separator. Oil separator is very important. Why? Because we mentioned that the oil, no matter how hard we try to keep it staying in the refrigerant, but just when the refrigerant is discharged out of the compressor, there will always have some oil mix. That's we can say mix, right, with the refrigerant, and it will be take out. So, but the oil is only good for the compressor. As compressor without oil, it will damage. But the other components or other area in the whole system doesn't need it. So that's why we design several type of oil components or oil control logic to bring the oil back from the system to make sure the system can the compressor can have efficient oil to get smooth, right? So oil separator here, normally we say that 99% of the oil will be separated, and then it will take over the oil back to the compressor. Here it's the inner structure of the oil separator. Here we can see that this is the inlet and all that. Here there are two small pipes. One is connected to the capillary and then go back to the compressor. Another one is connected to the SV4 we mentioned, right? The SV4 valve. One is for continually oil return. Another one is SV4, we can call it fast oil return. Here it's how the oil separator working. The mix of the refrigerant and oil which come from a compressor will enter the oil separator from liquid pipe. The mixture will flow a guideway. The mixture will hit to shell and flow spirally. The oil will be separated due to centrifugal force and force down along the shell to the bottom. So the refrigerant gas will go to the outlet pipe and enter the heat exchanger with a oil-less status. Okay, so this is the discharge side, the high pressure side. We have the oil separator accumulator that we install it in the low pressure side, right? So here, apparently, it is used to separate the gas refrigerant and the liquid refrigerant. This is a little upside down. The refrigerant come inside. This one will be lower. This pipe will be higher. So it can make sure by this design we can make sure that only the gas one can reach to this hole, so it will goes from the top to this pipe and go out. But the liquid, we can make sure it cannot come up. Okay, so that's the components that I want to introduce to you. Mainly, we can say we have 4 key components, and we have some valves, solenoid valves. We have some pressure sensor, pressure switch, and we have the oil separator, we have the accumulator. So by all these components, some is for control the refrigerant volume, some is realize the throttling, some is protection the system, some is for getting the running parameters. So by forming all this design and components in the system, so we can make our system keep running more stably and getting a good performance. So do you have some questions? If not, we will go to the third part. It's about some essential control. Essential control, we will have 4 parts. First one is the distribution of the load. Second is the crankcase heater. Third part is fan speed. Fourth one, it's common protection control. This one, I think you are familiar, right? When the system is first, we need to see we have an inner side load requirement calculation inside that we will get the total indoor load from the indoor side. Here, if the total here we can see we have 3 auto units. Largest one is 32 horsepower. The second one is 30 horsepower, and the next one is 22 horsepower. So when the indoor side is 32 horsepower, then only need to run 1 auto is enough. So this time it will run number 1. But when the indoor capacity demand reach to 81 horsepower, then it's over 1 auto. So in this time, our VRF system right now we do not support to run only 2 auto units or 3 if the system is a 4 combination. For a 3 combination one, then we need to run 1 auto unit or turn on the whole system. So in this time, we need to run 3 auto units, and we need to distribute the proportion. How to do the distribution? 32, 30, 32, 30, 24. It's 90, right? 90 horsepower total. So 81 it's 0.9. So 0.9 multiply 32, you will get 29. 30 multiply 0.9, you will 27. 28 multiply 0.9, then you will get 25. So our R&D will have a table that it will showing the auto capacity and the demand it's needed and the frequency. What is the frequency correspondingly? So according to the distribution, then each auto unit will know what is their target frequency needed to run. Crankcase heat exchanger is used to ensure the lubrication effect. It's adjust according to the ambient temperature and the discharge temperature. Here we can see when the ambient temperature is lower than 35 and the discharge temperature is lower than 40 degrees, then the heater will turn on. But when the ambient temperature is over 40, or when the discharge temperature is over 50, then the crank heater will be off. Fan speed. First, we need to say fan is very important, right? Because when we do heat exchange in the condenser or in the evaporator, we all need the fan to help the heat exchange. So how it operate, how it act, it will have an initial speed, fan speed, according to the ambient temperature. Normally it will be few seconds earlier start. Then the compressor, and after the compressor stops for 1 minute, then the fan will turn off. We mentioned that we wanted to keep the system pressure in a good value range for keep the compressor and the whole system efficiency in a best status. But we need to adjust the pressure because the system is changing all the time. Sometimes it will out of our best range. So how to control it? It's by the fan to adjust. The initial one, as I mentioned, it's according to the ambient temperature. When the ambient temperature, here we can see the ambient temperature more higher, the fan speed will be higher. We have 35 steps. Here we can see the fan speed in cooling. It's according to the discharge temperature. And for example, when the outdoor heat exchange is not good, so P1 will showing, right? So in this time, we will increase the fan speed. When the heat exchange improved, be better, then the pressure will drop. Here we can see it's the speed we want to keep. And when the pressure is high, then the fan speed will increase. When the pressure is low, then it will decrease. And the system will detect the pressure every 10 seconds. Okay, system we have lots of protection. P4, it's here. Discharge temperature pressure protection. It's when the discharge temperature is over 120 degrees, it will have the error code. But when it's recover back to 90 degrees, first we will limit the compressor frequency, right? Or it will not just directly turn down the compressor. It will try to limit the frequency. Okay, the second protection code, it's the C7, inverter module protection. We have a sensor to detect the inverter module board, the temperature of it, because it's used to drive the compressor, so and it's expensive too. So we wanted to keep the system running at max. So we designed the protection for the inverter module too. So here we can see when the discharge temperature is at a certain value, then it will start to limit the compressor highest running frequency. And for the inverter module, similar. If the temperature is over 74, it will limit the frequency. After limited frequency, its bit still go higher, then the error code will show. But if limited frequency it's dropped back, then it will go back to normal operation. So for compressor, that we have several protection. We have current protection. We have the inverter module compression protection. Okay, so this is for some essential control for the system. Also, our last part is 3 special operation in the VRF system. First one is oil return. Second one is defrosting. Last one is duty cycling. First one, oil return. Oil return is always VRF system a very important point because VRF system, the pipelines, it's normally not short. So in this time, the compressor oil return will turn into very important because when the compressor is lack of oil, it will burn down. And we have the oil return process. It's to make sure the compressor has efficiency oil. So for V6, we have 4 steps. Compared to V5, we cancelled 1. We don't need it, so we only have 4 steps. First one is the oil itself, compressor itself. Second one is the oil separator we introduced. 99% will go back. And the third is for the unit, which has 2 compressors. So it's the balance between the compressors. And the fourth one, it's the program written in the software. Initially, it's 140 minutes, sorry, not meter, minutes, and then after 8 hours, it will run the oil separator. Here is the table showing when the system is entering into oil return, we will have the arrow, not arrow, the digital LED will display that DO or D0, DO, D0, that showing that the system is entering into oil return process, and the components for the fan and the EXV, how it will react, showing as below table. Outdoor, how the components will work, it's showing in this table. Okay, this is the oil return. Then it's the defrosting. We know that when the ambient temperature is low, in heating, the outdoor heat exchange is working as evaporator, so it will be easily get frost, right? And if the frost is going, then the heating capacity will drop as the frost getting more, so the heat exchange will be more worse. So for improve the heating capacity, the defrosting will be very important. We have the logic that reach to what condition that the system will enter into the defrosting operation. Here it's the condensing temperature, it's reached to 15 degrees. When it will exist, it's when the defrosting operation is running over 10 minutes, then it will exist. Okay, last one is the duty cycling. Duty cycling, I think you all know about that, right? It's when the system has lots of auto units, we will have the duty cycling. When the system only need to run one auto unit, so we will have this operation. For example, when we reach the oil return, or when we reach our setting temperature, the compressor stops. Or after the defrosting here mentioned, then next time it will turn to the second auto unit to run for keep a balance of the whole system. And of course the compressor itself too. So oil return, defrosting operation, and duty cycling, it's the three special operation we design in our system. So get a conclusion for our V6 unit that we have a very strong principle design, and we have adopt high reliability and high quality components to make the system working and assembled. And we have designed lots of smart control logic to keep the system running stable and more intelligence, and lots of protection too, for keep the owner or customer to use more convenient and reliable. Okay. Sorry. So, okay. So that's the whole key component